In this lesson, we'll first look at how the law of definite proportions can be used to determine the mass percent of elements in a compound. We'll also look at how the law of conservation of mass allows us to make predictions about the number of grams of substances needed during a chemical change. In the second part of today's lesson, we'll be looking at what happens when substances are combined without any chemical changes occurring. Because the concentration of the different components can vary, we can no longer write a formula for the combination. We no longer have a substance. And this combination of substances is called a mixture. We'll then look at the different types of mixtures and then some of the techniques that can be used to separate mixtures back into their component substances. By the end of the lesson, you should be able to calculate mass percent, identify the type of mixture that is present, and justify how a mixture could be separated based on differences in physical properties. So the law of definite proportions is pretty much based on the fact that when you have a chemical formula, you always have the same ratio of the elements. So that means that the ratio of their masses is always going to be the same. So if we look at the mass percent of hydrogen and oxygen in water, in general, whenever you determine percent of anything, it's going to be the part that you're interested in this case the mass of the element, divided by the total mass, or the total, times 100. So if we wanted to determine the mass percent of hydrogen and oxygen, given this information, we would then do, let me find my pen. We could write it out and say that, well, I got 0.11 grams of hydrogen, and then we have the total mass, which is 0.11 grams plus 0.089 grams, so 1 gram, times 100, and we do the math, and we end up getting that we have 11% hydrogen and 89% oxygen. You could either calculate it again, so you put 0.89 over 1 times 100, or you could just say, well, I know there's only 2 components in there, so the percentages have to add up to 100. So 100 minus 11 gives me 89% oxygen. Now, if we wanted to do a slightly more interesting problem, how many grams of hydrogen and oxygen would be in 10 grams of water? Now, if you think back to a previous lesson, we saw that mass is an extensive property. So therefore, since we have 1 gram of water, let me get my highlighter. Since 1 gram of water has 0.11 grams, that means if you had 10 times as much stuff, it would be 10 times as much hydrogen and 10 times as much oxygen. So if we had something that was a little bit more interesting, wanted to figure out what it is in 59 grams of water, you could do, well, it's 59 times that initial information. But if all you had was the percentages, you can say, all right, well, I'm going to take 59 grams total times the 11% in decimal form. Remember, you have to convert it back into decimal before you can multiply it. And that gives you, oh, where'd it go? 6.5 grams of hydrogen. And then if you do the same thing for the oxygen, it would be 59 times 0.89, and that gives us 52.5 grams of oxygen. Conservation of mass, may as well bring it up since we're talking about this sort of stuff with substances. The conservation of mass statement tells us that matter is neither created nor destroyed during a physical or chemical change. I like to summarize this by saying what goes in must come out. So we have an example here. We have 23 grams of sodium metal is reacted with 35 grams of chlorine gas to form sodium chloride as its only product. What was the weight of the sodium chloride that was formed? So typically when you see these kinds of problems, it's better to get the numbers out of the word problem just to reduce some of the visual noise. And so we say, all right, well, I know that the reactants are going to react and combine and do their thing to form the products. So my reactants were the sodium and the chlorine gas, and it formed the product sodium chloride. So now I write the numbers down. We had 23 grams of sodium, 35 grams of chlorine, and so you say, all right, well, how many grams of sodium chloride? Key there is that it says that it has sodium chloride as its only product. So that means all of the sodium and all of the chlorine gets used up. So it's just a matter of adding them together. So you had 58 grams of stuff going into the reaction, and you better have 58 grams coming back out of the reaction. Another way to look at a law of conservation of mass problem is given in this word problem. We have 100 grams of lard is reacted with 50 grams of lye to form glycerin and soap. So how much soap was formed if we had 25 grams of glycerin produced? So again, let's pick these numbers out of the problem. So we have our reactants going to form the products. We have lard plus lye gives us glycerin and soap. That was given to us in the problem. Now you write down the numbers you know. So we had a total of 150 grams going into the reaction. There's 25 grams of it was the glycerin. So that means that the soap you would produce 125 grams of soap. So now let's go on to mixtures. So a mixture is a combination of two or more substances. The composition of the mixtures is variable. So if you were like looking at this picture up here, you could have a mixture of one screen bean in the blender full of water, or you could have 2 screen beans in the blender of water. The composition changes depending on how many things you mix together. So there are 2 different types of mixtures. We have a heterogeneous mixture. That's where you can see different parts in the mixture. It doesn't look like one thing. So for example, if you take a bottle of water and you're playing a prank on a friend and you dump some sand in their bottle of water and you mix it up, you're going to end up with sand in a bottle of water because it is a heterogeneous mixture. The sand does not dissolve. On the other hand, the other type of mixture would be a homogeneous mixture, or homogeneous. A mixture is one in which it looks to be one thing, but you can have different concentrations, so therefore it is a mixture. So looking back at our bottle of water again, say you have those flavoring packets for your bottled water. There's some people that like a little bit of flavoring, some people that like a lot of flavoring, so you can have different concentrations, but it looks like it's all one thing. Now, a term that I'm going to be using most of the time, rather than homogeneous mixture, is a solution. A solution is, when you say solution, it is synonymous with a homogeneous mixture. And it's much easier to say. So there's a whole bunch of different types of solutions depending on what you are mixing together and the state of matter of the different components. So we have an example of a gas-gas solution would be air. A lot of people think air is just one thing, but if you think back to like middle school science, earth science, you know that air is 78% nitrogen and 21% oxygen and 1% everything else. So you can say, all right, well, these aren't chemically bonded together. It's just separate nitrogen gas and oxygen gas. Whenever you have a carbonated drink, that's when you have a gas-liquid mixture. An example of a liquid-liquid solution is vinegar. Vinegar is actually a fairly dilute solution of acetic acid. It's only 5% acetic acid and the rest of it is water. And then the most common type of solution is when you dissolve something in a liquid. So sports drinks are my example there. So we have the ones that have sugar in them are typically 0.1% sodium chloride, 5% sugar, and 94.9% water. The 0.1% sodium chloride is the electrolytes that they're always talking about in the advertisements for the sports drinks. And then you can also have solid-solid solutions. For example, first you have to know that pure gold is 24 carats. It's kind of a weird unit. But an 8-carat gold ring, so you're going to be a pretty cheap gold ring, is a solid solution of copper, silver, and gold. So the fact that the copper is present is why if you have really cheap gold jewelry, it turns your fingers funny colors because your skin oils and your different components on your skin are reacting with the copper part. All right, so some vocabulary. Viscosity is a fluid's resistance to flow. That is the official definition. My students usually end up saying it's how gooey something is or how thick something is. If you ever heard the phrase slow as molasses in January, you know that, so that's just giving a way to remember that viscous fluids have a high viscosity. So slow as molasses in January, you know that viscosity increases as temperature decreases. And so in the next bit, I have a little media clip where they're showing you the different weights for motor oil and how they flow, how their viscosity changes depending on the temperature. And the temperature in the room is minus 40 degrees C. All right, so obviously the one on the left is the one with the lowest viscosity. When I moved to South Dakota from North Carolina, I was very concerned about whether the oil in my engine was going to be okay for the winter because in North Carolina, what they used most of the time was this 10W30 weight. And so if it got kind of cold, that's sort of gooey. I really want to have that in the engine. Actually, it turned out that the manufacturer for my car had already specified that I should always be using the second weight motor oil. Those numbers, the first number corresponds to the viscosity of the motor oil at low temperatures, so when the engine's cold, and then the second number corresponds to the viscosity of the motor oil at a high temperature. So separating mixtures. Sometimes you have a sample of something and it's a mixture of a whole bunch of different things and you want to separate them out so you can test each component separately. The way you separate mixtures is by taking advantage of differences in physical properties. So here I have my screen bean that was in the blender. He didn't want to get blenderized by the devil's screen bean. So he is being physically removed from the blender. So that's an example of a physical separation. If you had a bunch of different colored marbles, for example, and you wanted to separate them, you would use a physical separation. You'd pick them up and move them to separate piles. One of the most common ways that people use to separate solids from a liquid is filtration. If you ever make coffee with a coffee pot, you know that you have to have that coffee filter in there in order to keep all of those coffee grounds from ending up down in the coffee pot. You also know that even if you have a filter in there, you're always going to get a little bit of really fine coffee grounds in the coffee pot anyway. And that's because the filter can only stop particles that are bigger than the pores through the filter. So the ones that are smaller, the really, really fine grounds, are going to go on through the filter paper. So distillation is a way to separate substances based on differences in boiling point. One of the places I lived in, I've lived in 7 different states in a whole bunch of different places. One of the houses I lived in was kind of across the street from a distillery. And you could always sort of get an idea what they were distilling that day because the uh, aroma in the air would be different. I kind of like brandy days because on brandy days they would put wine into the flask and then they would heat it up using something other than a Bunsen burner. And the alcohol in the wine starts boiling first. Turns into a vapor. Up here, it's much colder. We have cold water going around the outside of the condenser tube, causes the alcohol to condense back down into liquid alcohol, and then gets collected over on the other side as a concentrated alcohol. It's called the distillate. The thing is that some of the flavorings in the wine also have low boiling points, and so they get carried over as well. So the key thing with distillation is that the substance with the lower boiling point will distill off first because it starts boiling first. All right, crystallization is another way to separate a dissolved solid from a liquid. You take your solution and you just let the solvent evaporate away slowly. The slower you can get that solvent to evaporate away, the bigger the crystals will be. If you ever tried to make rock candy, you know that this is not as easy as it might sound. So I have a picture up here. It's just sodium acetate crystallizing off of a seed crystal in an aqueous solution. I also have, try to see if I can get this to work right, 2 videos. One video is sodium acetate dissolved in water. Nope, it's not working. Let me see. Oh, there we go. So the one on the right is sodium acetate dissolved in water. It's actually a supersaturated solution. And the one on the left is essentially mothballs dissolved in chloroform. He's going to put his solution on a microscope slide so we can watch the crystals form. These are both done in real time. So over here you can see the sodium acetate crystals forming. You can tell it's a solid because you can't see through it. And over here you can see these rectangular paradichlorobenzene crystals forming as the chloroform evaporates away. All right, so here's another separation technique. It's called chromatography. That's where you separate 2 dissolved substances based on their solubility in the solvent. So what this image is we have, it looks like aluminum oxide. It gets pressed down onto a plate. So this is called the stationary phase. And then we have a dot of blue dye over here on the left, dot of yellow dye over on the right, and a combination of blue and yellow dye in the middle. And it's the end of the plate is dunked into some solvent. The solvent travels up the plate by capillary action. And get the video started so you can see what happens. So this darker level is the solvent, and you can see that the yellow dye is pretty soluble in the solvent. It's traveling almost as fast as the solvent is. But this blue dye does not want to dissolve in that solvent. And so our mixture here, we're going to be able to eventually separate the yellow from the blue. I had a colleague that was using chromatography, this kind of chromatography, to separate out his product that he was trying to get. And he would have like 10 plates set up around the room. And then he would go along and he would scratch off all of the aluminum oxide that had the product band in it that he wanted. It was a very labor-intensive process. All right, so now we've got an understanding check. So again, pause the video and see if you can figure out how you would separate these mixtures and then see if you're right. So the first one, sand and salt. All right, so the physical property that's different here is that salt is soluble in water, but sand is not. So you can just dissolve the salt, put them in a beaker of water, and then filter out the sand. And then sand and iron filings. The big physical property that's different there is that iron is attracted to a magnet, sand is not. So you could just use a magnet to physically remove the iron from the sand. Then we have red and blue marbles. I already used those as an example, so that would be a physical separation. So water and salt. So you're going to have a homogeneous mixture because salt water just looks like regular water. So you could boil off the water and whatever's left behind would be the salt. So that's kind of like a distillation. And then water and alcohol. And the hint here is that alcohol feels cold on your skin because it has a low boiling point. It's absorbing heat from your skin in order to get it to allow it to go from the liquid to the gas phase. So that would be another distillation example. And then the alcohol would come off first because it has a lower boiling point. All right, so our wrap up. Substances have a fixed composition and consistent properties. And that's because of the law of definite proportions, and we can calculate mass percent. So that's that one. And then we can also use the law of conservation of mass in order to work with some more, because we know that matter is neither created nor destroyed during a chemical change. And remember what I said as a summary was what goes in must come out. Unlike substances, mixtures have a variable composition, which means that they're not chemically combined. So we can separate the mixtures into their component parts by using differences in physical properties. There are two different types of mixtures. We have homogeneous mixtures, which are also called solutions, and they look to be one substance, even though they are actually a mixture. And then heterogeneous mixtures, you can see the different parts. You know, it can be something like oil and water, where you can see the oil floating on top of the water because they won't mix. And then the separation techniques that we looked at, you have physical separation, filtration, distillation, crystallization, and chromatography. So that's it for our discussion about mixtures. Thanks for listening.